Hi guys, and welcome to this evening's video, which is all about forces. We're going to review how to draw free body diagrams, how to calculate the net force on an object, and also how to find that object's acceleration. So throughout this video, I'm going to be doing a couple of example problems with you, and the final problem will be one that I would like you to do on your own. If you take no other notes during this video, at least do the example problem that I want you to do by yourself, and then we can check it tomorrow in class. There will be time markers in the notes of this video, so if you would like to fast forward just to those particular examples that you would like to try, you are more than welcome to do that. So, let's go ahead and get started. And just some basic reminders that you probably learned last year about forces. A force is a push or a pull. I think you guys learned that in 8th grade. But I like to say it's the cause of an acceleration of an object. So forces are vectors. They can be positive or negative, and their direction always matters. So when you're adding up the net force on an object, you need to take into account those directions. Free body diagrams, I call those FBDs. This is when we sketch all of the forces acting on an object. So it is a summary of the problem, in a sense. It's a picture of the situation. And then some kinds of forces we'll be talking about are normal, gravity, tension, the applied force, friction. There are two different kinds of friction. Remember, there's static and kinetic. And then we're also going to talk about buoyancy. Not so much in this chapter, but in the second 9 weeks, buoyancy is another force that we're going to start to investigate. So, another review on Newton's laws. Objects in motion will stay in motion unless acted on by an outside force. That means that an object at rest will also stay at rest until you put a force on it to make it move. The second one is the big one, F equals ma. And then the third one is also really important for some of the problems we're about to do, that every action has an equal and opposite reaction. Remember, if you guys don't remember, that weight is the force of gravity acting on an object. So if I want to find an object's weight, I need to take its mass and multiply it by the acceleration due to gravity. So if I weigh 100 kilograms, that means that my weight is about 1,000 newtons. Okay, just another review on friction. The coefficient of friction, remember this is a unitless number, so it's just really a ratio. And it depends on the surfaces that are in contact. So if you have glass on glass, that coefficient of friction for a glass surface is going to be different than the coefficient of friction for, say, sandpaper or something rougher. So static friction is used to describe the force necessary to put something in motion, and the kinetic friction is used whenever the object is already in motion. But it's just a ratio, as you can see down here, between the frictional force and the normal force. So it's between the surfaces that are in contact with one another. Now the static friction, coefficient of static friction, will always be larger than the coefficient of kinetic. It always takes a lot more force to get something to move than it does to keep it moving. And anybody who's ever moved really large furniture knows that experience pretty well. Okay, so here's some problem-solving strategies when dealing with net force problems. The first one, of course, is to always draw a picture. Draw your FBD with all of your forces labeled. As long as you've labeled all of your forces correctly, there's no way that you can get the problem wrong, because all you have to do is find those individual forces and you're set. Remember that if the object is on an incline, we need to replace that weight vector with its x and y components. And we're going to see an example here in a second. Determine the net force on the object, and this fourth one says use Newton's second law to write an expression for the acceleration of each object. Now sometimes in these problems we're going to have a multi-object system. So we're going to have 2 or 3 objects that are experiencing forces at the same time. So make sure you're drawing an FBD for each one of those objects and that you're expressing their acceleration uniquely. So here are the examples that we're going to do. And they start off pretty easy and they get progressively trickier until the last one. So let's look at the first example. This one is a hockey puck of mass 1/2 kilogram. So I'll give you guys a second to read that, and let's go ahead and take a look at how we go about solving it. So we have a hockey puck that has a mass of 1/2 kilogram, and it has an initial velocity of 10 meters a second. And it slows to 2 meters a second over a distance of 80 meters. So the problem wants us to figure out what is the frictional force on the hockey puck And then what is the coefficient of kinetic friction between the puck and the ground? So the first thing we're going to do is we are going to draw a free body diagram. Here is hockey puck. There's no need to actually draw an object. You can just draw a square or a circle. It doesn't matter. So we have the force of gravity acting straight down, which should be on every single free body diagram that you draw. We have the normal force acting upwards. Now this hockey puck is not going up or down, it's going straight across, so these two vectors should be equal and opposite from one another. I know my picture doesn't look it, but they are. Now, if this object, let's say this object is sliding in this direction, right? But it's slowing down. So the direction of its acceleration is actually going in the opposite way. So if this is the direction of the acceleration, that's also the direction of the force. So what is slowing this hockey puck down is the force of friction. So we have the normal force acts against the object when it's at rest on a surface. Gravity always pulls it down, and then we have our force of friction. So that means if these two guys cancel out, that the force of friction is equal to your net force, which is equal to m times a. So we know our mass from our problem is 0.5. We just need to figure out the object's acceleration. And from what's given to us in the problem, we can do that with a little bit of kinematics. So we have VI, VF, and change in x. So we can use this. If we substitute in our 2 squared equals 10 squared plus 2 times 80 for our distance times our a. So when we do that, we get an acceleration of 0.6 meters per second squared. And this is, of course, negative because it's slowing down. So now that we know our force, now that we know our mass and our acceleration, we can plug this number back into our equation, and we get that our force of friction is equal to 0.5 times negative 0.6, which should be 0.3 newtons negative. Alright, now they want to know what is the coefficient of kinetic friction between the puck and the ground. So we have the first part of a kinetic friction ratio. We have the force of friction over the normal force. So we have this part. We just need to figure out our normal force. Now remember what I said, that the normal is equal and opposite. So the force of gravity is m times g, which is 0.5 times 10, which is 5. So the coefficient of kinetic friction ends up being 0.3 divided by 5. Which ends up being about 0.06. Now remember, the coefficient of friction is unitless, so it's just a number. It just represents the ratio. And that's the answer to the first one. So, continuing on, let's look at the second example. Kevin has a mass of 60 kilograms and decides to test Newton's laws of motion by standing on a bathroom scale placed on the floor of an elevator. So take a second and read what the question is asking us to solve for. And then let's go to the whiteboard and take a look. Always try to do these before I do them, so you guys can check your work. So here's Kevin. He's in an elevator on a scale. So let's draw a free body diagram that shows what Kevin is experiencing. So he's got a weight down. We're going to do this for the first scenario where it wants us to do it with the acceleration upwards of 0.5 meters per second squared. Okay, so he's always got gravity, right, pulling him down. Now he's got an upward force, right? Say it's done by the scale because he's standing on the scale. And in this case, since he's accelerating upwards, this upward force by the scale has to be more than gravity. If it wasn't more than gravity, he would fall, right? And he's not falling, he's accelerating upwards, so this has to be greater than your force of gravity in this particular case. So he's got two forces acting on him, and they're acting in opposite directions. So remember that net force is always m times a. So for him, his net force is actually the force of this scale minus the force of gravity. Is going to get him m times a. Now, we know all of these bits except this. So let's go ahead and put force of gravity is his mass, which I think was 60, times gravity, which is 10. And then his mass here, 60, and then his acceleration is 0.5. Alright, so this becomes 30, and this becomes 600. Right? So that means that the force on the scale is 630. Alright, let's look at the next part of the problem, which wants us to figure out what it is when he has a constant velocity of 3 meters per second. Now remember, if the velocity is constant, there is no acceleration happening. So we're going to have the same exact setup, scale minus force of gravity, except now those two things, when we subtract them from one another, is going to equal 0 because there's no net force, there's no acceleration happening. So this guy is 600, we already figured that out, so that must mean that the scale force is 600 as well, in order for that to equal 0. So let's look at part C. Part C says, what is it when the acceleration is -1? Again, same setup, because the free body diagram hasn't changed any, right? He still has the force of the scale and his weight. Now he has an acceleration of -1, so that's what's going to go there. So this again is 600, and this becomes 60, so that means that the force on the scale is 540 newtons. Alright, let's look at the third one. Third one, this is an angled problem, so we have a plank at one end of an angled ramp that is 30 degrees. So go ahead and pause the video and write down what you need to, and give it a try before you watch my solution. So here is our angle. Ooh, that is much more than 30 degrees, but that is alright. We'll roll with it. Here is your block on this angled situation here. So let's take a look and draw the free body diagram for our block. It has gravity going down, of course. It has a normal force. Remember, the normal force acts perpendicular between the surface and the object, so instead of going straight up, it's going to kind of come up at an angle because the box is sitting at an angle, so we're trying to make it be perpendicular here. Now it's sliding downwards, so we do have a frictional force that's acting against the motion, and it's acting up the ramp here. So there's our friction. So the first thing we need to do is separate our gravity vector into x and y components. You guys might have learned to do this differently depending on whether or not you had me or Miss Harrell. For the x vector, I like to use cosine, and if this angle is 30, then this angle of this triangle is 60. And then for the y vector, I like to use sine for y. So again, that will give us the force in the x direction, and then that will give us the force in the y direction as well. So now we can redraw that free body diagram. Once we split these up, we can redraw that free body diagram so that it is not having anything act at weird angles. So here's our normal force, and here's our y component, and here's our x component of gravity, and here's our friction. Now we have four forces that are acting perpendicular or parallel to one another, and it's much easier to subtract them and add them together. So let's go ahead and take a look here. Your y component is going to be 2 times the sine of 60. And then your x component is going to be 2 times 10. Alright, so that means that
2
our
times 10
force
times
in
the cosine of 60.
x direction then is about 10 newtons. And then in the y direction, we have sorry guys. My computer is acting funny. We have a force of about 17 newtons. So that means this is 17, and that means this normal force is 17, and this x direction is 10. Now, since these two guys are going to cancel out, all we need to figure out is our force of friction, and then we can have our net force, because the force of friction subtracted from our x vector here is going to be our net force. So remember, coefficient of friction is force of friction over normal. And in this case, our coefficient is 0.2, and our normal is about 17 here. So when we do that, we end up with a frictional force of about 3.4 newtons. Now, frictional force of 3.4 newtons. Now, to figure out our net force, we have to subtract our x down and our friction up. So 10 minus 3.4, that's going to get us about 6.6. Now, the acceleration of the box is going to be equal to our force divided by our mass. So 6.6 divided by 2, we get about 3.3 meters per second squared. Now for the last part of the problem, where it wants to know what is the speed of the box at the bottom, well, we're going to have to do a little bit of kinematics for that. If we assume the initial is 0, the A is 3.3, and the VF is what we don't know, but the distance they tell us is 1. So that, when we do that mathematically, which is going to be our VF squared equals VI squared plus 2AX equation, that gets us to 2.5 meters per second. Alright. Let's go back and take a look at the next example. Now I'm running really short on time. I know I'm running over the 15-minute limit, so I want to give you guys a second to read this problem, and then I'm going to draw a free body diagram for you so that y'all understand what you're trying to find. And then I'd like for y'all to try this one and also this number 5 on your own. So go ahead and pause the video if you need to write down what's happening in the problem. In this one, I will draw it for you real fast. Here you have an incline, and you're going to have one box here, and then this is kind of like a pulley, and it's connected by a string with another box down here, farther down on the ramp. This one is 10 kilograms, and this one is 7. Alright? And then this angle here is 30. So let's go back and look at the other one, and I'll draw a picture of this one too. I'll give you guys a second. In this one, what we have is a pulley situation, so we're looking at tension. So down here is Brandon, and he's holding one end of the rope, and then on the other end of the rope is a 200 kilogram set box, and Brandon has a mass of 75 kilograms. And I want to know what is Brandon's acceleration. So go ahead and give this one a try. Give the other one a try. I apologize for the long video, guys, but I had to work out these examples for you. And I will see you tomorrow.